Alright everyone, welcome back. Today is our second day of 3D rigid rotor, 3D rotational quantum mechanics. This is, let's see, we've got 2 more days, including today, where we're going to have equations that just go on and on and on. There's today, you got a good wallop of that yesterday, last lecture. And then we're going to see it one more time when we do the hydrogen atom. The hydrogen atom Hamiltonian is as big as what we did the other day, except it's actually bigger. And we're also going to do separability on the hydrogen atom, and that will actually be next lecture. And so, but as much as that will be quite a mouthful, we're done with it after that. You will not see Hamiltonians anymore, probably the rest of your life. Although typically we get 2 or 3 people going to grad school, and often 1 person in physical chemistry, so that person will see it again. And with that, I guess just go ahead and do some review. Actually, I definitely will end the lecture a little early today, but I think that's okay given the nature of the material. You might need to watch it more than once. And again, that's one reason I was making these videos for many, many years, it's just that this is material that there's no good analogy. It's just watch it over and over again, and you accept it. Now, I know that certainly sounds like brainwashing, but to the best of our human ability to tell, what quantum mechanics tells us has always been correct, and we can design things with it. We can design circuits, right? Circuits have electrons, and electrons being low mass behave very quantum mechanically. Circuits work pretty well. That's why we have iPhones, right? And with that, we have nothing else. We don't need anything else. But none of this would be possible without basically, it's like we use supercomputers to design supercomputers. And it all is quantum mechanical. If you don't incorporate quantum mechanics, then none of your modeling or whatever, none of it will be accurate. Okay, anyway, so motivation. All right, 3D rigid rotor. Take kinetic energy, partial double derivative of x, plus double derivative of y, plus double derivative of z. Turn that into r theta phi. Right, so recall that our coordinate system, maybe I'm showing that there, our coordinate system is 3-dimensional now. We have a vector, and the projection of that vector is phi in the xy plane. And the one that's always easy to remember is theta is with respect to z. So this is our theta guy. And I don't expect you to memorize this, but that's the one that always goes from 0 to pi. And theta goes from 0 to pi, and phi is 0 to 2 pi. So, and I'm just saying that to remind you of how that works so that you're comfortable. Anything on an exam that requires that, I would tell you, because you can Google that pretty readily. And I don't see the point of hiding that kind of information. All right, so that's our coordinate system. So we turned the Cartesian to spherical, and then we started working on separability. Now, separability means I'm going to write out the wave function not in x, y, and z, but r theta phi. And because we're not on hydrogen atom yet, hydrogen has its electron like on an elastic band, so it can move around in the r direction. We're not there yet, so we're going to do the 3D rigid rotor, and so we're going to assume that the wave function in the r direction is fixed. It means that the string is rigid, basically. The radius is fixed. And so all the DDRs, double derivatives of R's, they all are 0 because they're acting on, you can either say that there is no radial wave function, you can just say it doesn't exist, so you can't take the derivative of nothing, or you can say that the wave function is just a constant, in which case the derivative is still 0, the derivative of a constant 0. So that simplified things. Not really, right? Anyway, okay, then, having eliminated all the r parts, we then worked on the thetas and phis. Now, we did this by trying to show separability, assuming that the wave function is something with phi times something times theta, assuming that. Acting on the right, dividing out on the left, which is equal to the energy. Now, normally I'd have the energy times the wave functions, but remember I divided by the wave functions. Now, and another thing I like to do to go into the lane of mathematics, I usually like to bring E over and set it equal to 0. And the whole, a lot of the ideas behind separability of how I'm going to get like miniature Schrodinger equations is a little bit more clear to me, because I see that if everything's going to be 0, then everything's a constant and it turns into its own Schrodinger equation. And now I'm describing in words what I'm supposed to be writing down. So I'm going to stop there and remind ourselves, let's see. I am going to go back. I'm not going to do the whole thing over again because that's nuts. I'm going to start where we are next to last part from last lecture. Now, recalling that this is what we did and looking at your notes, what we ended up with, we ended up separating the wave function into, so it worked. It's separated into phi and theta components. So, you know, I can't, I'd like to review from the very beginning, but it would take all lecture. On this one it would. Other things not so much. Okay. Now remember that we manipulated the sign. This is the phi part. The theta part had a 1 over sine squared. There was a 1 over sine. Sorry, there's a 1 over sine theta here. So we multiplied everything by sine theta, which is why I have this here. And sorry. I gotta look at my notes. Okay, that's from dividing through by the wave function. And then we get, there's a pattern here now. I don't expect you to memorize this, but it's always d theta, sine theta, d theta, wave function theta. So, as much as it goes across the board, again, there is a bit of a pattern to it. It makes it a little bit less, you know, hideous. Okay, and again, I like to bring over the energy term. But recall that, where's the h bar? Where's the moment of inertia? Remember all that? So you may recall from last lecture that I did some factoring. I brought over the h bar squared, the minus h bar squared, and there's that sine theta I mentioned before, and sine theta squared. Now it's all equal to 0. Okay, so this was where we stopped at the last lecture. Cool that this is the phi part, and here's the theta part. Okay. Here's something, I didn't bring this up last lecture. For me, this was 10 minutes ago, but I usually film these two of them back to back. I don't know if it's better that way, but it's a little bit more convenient. But so what I said 10 minutes ago was, I did not mention this. What's kind of interesting about this being the theta part, is that energy is part of the theta wave function. You haven't seen anything like that yet. Well, we haven't done that many multi-dimensional equations. But usually, you know, it's a bunch of derivatives equal to energy. This time, because it's multi-dimensional, energy has gotten sucked into one of the mini Schrodinger equations. So that's a little different. So let me tell you how that plays out. It turns out that I normally would like to say that this contributes the phi part of the energy, and this contributes the theta part of the energy. That would be comfortable, and it's kind of sensible, but it's wrong. It turns out that the energy is solely determined by this miniature Schrodinger equation. So that's kind of a strange thing. This miniature Schrodinger equation is like the dominant one. It will determine the energy, and that's important. That's why I say it's the dominant one. This one basically serves to modify that one. It perturbs it a bit. And that means that it puts constraints on the energy. But make no mistake, this is dominant because it will determine the energy. Okay, so again, that's kind of a big picture to explain a little bit more about what I'm going to write down, which I'm going to start writing down the solutions. Right, now I've shown separability, now what? Okay, in terms of solutions, I mentioned this before. So I don't quite, this has always bothered me a little bit. We just assume that the two-dimensional solution, the two-dimensional rigid rotor solution, is the answer to the phi part. Why not? Let's do it. If you do that, then we can make progress. I have never been sure why that's necessarily justified or what would happen if you didn't do that. If you didn't do this, I don't know that there is a solution. Another thing is that the answers we get making this, if this is an approximation, we have, really 100 years of history of analyzing this. Remember, I just told you about, like, supercomputers designing supercomputers, and they would not be able to do so if this was wrong. That's absolutely, that would never have happened. This thing that we're looking at is instrumental to many, many different sciences, including quantum mechanics. Okay, blah, blah, blah. So let's continue with this. Now, I hope that our math skills are up to speed, such that you can look at this and just do it, right? Just evaluate it. The double derivative of even the IMV is going to be, well, here, tell you what, let me just write it out. Instead of just doing it by saying words, right? I know I'm terrible about doing that. Okay, so here's the double derivative, and you're dividing by, okay, so this ends up being minus m squared plus all of this stuff. Okay. Now, what does that mean? Tell you what, let me speed up time. I'm going to go ahead and write all this out, but I don't want to bore you too much. So this is all minus m squared, and I will, let me write that nicely. I'm going to speed up time and do the rest of it. Okay, so there we go. All right, so I just rewrote all this again. That's why I sped up time. Okay, again, assuming that the two-dimensional solution is okay here, this is what we get. All right, last bit, let me just wipe this out because I don't like it. That was minus m squared, so I'm going to put plus m squared over here. And recall that m is 0 plus or minus 1, plus or minus 2. Doesn't matter if it's minus because it's squared. Okay, so there you go. We have a solution to the phi. Now we're looking for a solution to theta. We now have this miniature Schrodinger equation, which definitely looks like a Schrodinger equation because you've got energy in it. So this is why this is dominant over the phi. Notice that phi isn't really, it didn't dictate energy, but it does modify it. Because now let me explain why. We have a differential equation to solve, and it's equal to 0, 1, 10 to the 4, 9, 16. Every time you pick an m value, you have an equation that then has to be solved. My understanding is that's how it's done. This is actually above my head in terms of mathematics. So what you do to solve this, pick a value of m and then go. Now, when you do that, you're obviously going to get a different energy. So you can see how the phi part has some oomph to it. It does affect the energy, but at the same time, it's not obvious, at least, how it directly contributes to it. So that's why I call the theta like the dominant Schrodinger equation, because it does dictate the energy, not that phi has no role. It has a minor role, but that's not where you calculate the energy. Okay, now you've heard me say a zillion times how you go look in an 18th century mathematical textbook, 1782, That's when Columbus sailed the ocean blue. I think that's right, not 14. Anyway, this was solved in 1782 because this equation ends up being important to a lot of fields, and I believe it was solved for fluid mechanics. I think that's what it was originally solved for. So you engineers, you've been around a lot longer than you realize, and that was, Pierre Laplace or something who solved this. And let's just get to the solutions. I don't have much else to say about it. I think it was kind of neat that it was solved so long ago, but I guess that's really all I have to say about it. Okay, so in terms of the solutions, recall that when we were talking about a 2D particle in a box, you ended up with two quantum numbers, an n sub x and an n sub y, because you were in 2 dimensions. The more dimensions you have, you might pick up more quantum numbers. That's the case here. So when this was solved, we've already got a quantum number, which is m, but when you solve this, you're going to pick up another quantum number. Every time we solve a Schrodinger equation, even a miniature one, we're going to pick up a quantum number. The quantum number, remember its role is, it has a bunch of roles. It basically tells you what solution you're talking about, ground state versus excited states. The quantum number is going to tell you what the wave functions are, but of course it also tells you what the energy is. The quantum number is often actually, I think every time, is inputted into the equation for energy. Once you know that once you have the wave functions. Okay, so in terms of the solution, so let's start writing down properties of the solution. Okay, first, you get a new quantum number, and that is L. Does that last sound familiar? L as an angular momentum. Remember how when you studied hydrogen atom in freshman, L of 0 was an S state, and L of 1 was a P state, L angular momentum. So you're seeing that here. We're going to be plugging a lot of this into the hydrogen atom, so this is actually the same thing. So an L of 0, you can think of that as an S state. So L goes 0, 1, 2, 3, 4, blah, blah, blah. We'll just stop there. Okay, so there you go. Okay, now recall that again, I've said it a zillion times, the theta miniature Schrodinger equation is dominant over the phi. The phi has the m quantum number. Now it turns out that whenever you solve this, you're going to find more than one answer. Now, if you have an L of 0, what you're going to find is that. Sorry, let me back up. Let's start with the lowest possible quantum number, which we're going to start with m because you use m to solve this one. So let's say m is 0. Okay, what you find is that L can be 0. All right, but then if you plug in bigger numbers of m, 1, 2, 3, 4, on and on, you're going to find more solutions. And so the way that works is like this. So you make all these solutions and then you find this pattern. M can be minus L plus 1, dot, 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 0, dot, 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 out to L, plus L. Okay. So for any given L, the M's are dictated. Sorry, that's why I'm saying that there's this hierarchy, that L, the theta, is dominant over the M, which is associated with the phi. Okay, so if L is 0, which we think of it as an S state, then M, if you look at this, has to be 0. Okay, if L is 1, so let me write that down. Okay, L of 0, therefore M is 0. Okay, and again, this dictates that. Let's do another example. L is 1. M can be, looking at this, minus 1 plus 1 is 0, all the way to L, which is 1. So you can have 3 M sub values. Last one, and we'll stop there. Of course, m could be minus L, which is minus 2. Minus 2 plus 1 is minus 1 to 0. And that's it. Okay. Now, I've already let the cat out the bag that this is like an S state. There's only one S state, but look at this L of 1. Guess what? That's a P state. There's 3 P states. Now, you know that, Px, Py, Pz. We saw similar behavior on the particle in a 3-dimensional trap. Remember that? 3 lectures ago? I already forgot. Okay, L of 2, what's that? That's a D state. There's 5 D states, right? It's all looking familiar now? Dx squared minus y squared, dz squared, xy, yz, something, something. I don't remember the 5th. So anyway, I hope that this looks familiar. So we've got that under our belt. Now with the wave functions, and I'll do the wave functions last, you can get the energy, and remember that the energy is dictated by the dominant quantum number, which is the theta quantum, the theta miniature Schrodinger equation. Theta is associated with L, so it is the theta dominant miniature Schrodinger equation that's going to dictate E. Right? L is associated with that one, energy is associated with that one, so therefore energy is going to be a function of the L quantum number. And that is, here we go, h bar squared over 2I. Okay, now there's an implication for this. M does not affect the energy. Now for the S state, so what? But for the P states, that means that actually M of 0 is PZ. Just let you know that ahead of time. The P's, PX's and PY's and PZ's, they're degenerate because they all have the same L. The D's are degenerate, they all have the same L. Of course, the D is higher in energy than the P, which is higher in energy than the S. But you knew that, right? Again, this is all some freshman hydrogen atomic structure coming back. Recall that you had to use a lot of that for organic, right? You remember how you had to think about how p orbitals overlapped or didn't, and benzene, this and that, resonances. So all that was with p orbitals. Now, I don't know if you had an organic. Maybe you're not required. Look, I'm not too sure. I should know that. Sorry. But if you do inorganic, you do a lot with d orbitals. And what causes them to not be degenerate is if they interact with other orbitals. We're going to get to that in a week. But for today, everything's degenerate. So, now what? Let's see. I do want to just express one last thing. I don't think I'll put this on a test or a homework. I'll just go ahead and tell you that. However, I want to throw some information at you to make this look more similar to what you've seen before. Let me express the energy as angular momentum squared over 2 mass. Right now, instead of a little j, I'm going to use a big J. Because we're in 3 dimensions, I'm not going to use the same little symbol. And that will be over 2 times the mass, but remember, mass in rotation world is actually moment of inertia, I. Mass times r squared. R is still fixed. Okay. So this is the case. Now that means that, like everything we've seen where we have momentum over 2 times something with mass, that J has to be like an operator. So this is like the total angular momentum operator. Now that can be broken down into components. Since we're in 3 dimensions, we talked about how we have the little j operator, which of course will be squared. There'll be one for x, which you haven't seen yet, and there'll be one for y. And I'm not going to really do anything with these. But I just want to point out that we're technically we have no potential energy. This is just rotational energy. Rotational energy is rotational momentum squared over 2 times the whatever, moment of inertia. And since we're in 3 dimensions, last time when we were doing just 2D, everything was just jz. There was no x or y. Now, that may not conform with some of your memory, because remember that when we were doing 2D, everything was in the xy plane. But recall that the angular momentum rotor is the axle. So when you're in the xy plane, your axle is purely in z. So that's why the total momentum was just the z angular momentum, because angular momentum is 90 degrees from the plane of rotation. That's just some of you had physics mechanics, and that's what you learned, and if you don't remember, then you're seeing it again. And we talked about it just a few days ago. It gets a little bit more complicated because, of course, now we're in 3 dimensions, and there could be an x and a y component. So there you go. All right, and I'm going to use that again, maybe a little bit later, but I don't see myself having throwing anything on an exam because it's a bit much. All right, now let's see. What else can I tell you? I'm going to take a moment, wipe out the board, and I'm going to start writing out the wave functions, and I'm going to throw a couple of computer images and remind you of what these look like. And yeah, okay, so give me a moment to wipe out the board, and then we're going to start writing down wave functions and doing what we can with the wave functions. So I will be right back. Okay, we're back. So I will try to do some nice computer graphics just because I can. You know, it's no good way to do this during class like normal because I'd have to like switch between PowerPoint and the board, and it just doesn't work so well. So one of the few times that hopefully some of this is actually a little bit better than not. I'm not convinced of that, but regardless. All right, so we're getting to the wave functions. Let's see here. Let me just maybe write these down and point out some things about them that I hope you'll find kind of neat. Okay, now remember, L will dictate M, and of course there's a normalization. Let's not worry about the normalization constants. When we do eigenvalue equations, I think I've pointed out to you a couple of times now, if it isn't obvious. When you do eigenvalue equations, the normalization never matters because it's always grouped in with the wave function. The eigenvalue itself, the thing you want, is always external to that. And you've done a bunch of examples where you've seen that. Okay, so I'm just going to say that there's a normalization constant, and there is, of course, a theta component, and there's, of course, a phi component. But we already know that phi is e to the im phi. All right. We'll start with 0, 0, and you'll see that. We know that this is an S state. And the S state is just the normalization. There's actually literally nothing to it. Okay, now you may notice that I've drawn a little circle here. This is basically the S state, the L0, M0, 3D rigid rotor state, the ground state. Now, what's really remarkable about this is recall that I'm looking at this, I'm not looking at this, but anyway, I'm looking at this. And in your mind, I bet you imagine this. Let's call a particle an electron, because why wouldn't we? I bet you're imagining it's whizzing around the circle. It actually isn't, and I don't understand this. It's not whizzing around. It has no rotational energy. The energy of rotation is L times L plus 1 times all that stuff. L is 0. The S state has no rotational energy, so it's not rotating. So why does it look like a circle? I don't really know. I've actually never really understood that. The best I can do is compare it to something that does have rotational energy. So let's go with that. What has rotational energy? An L of 1 state, which we know is a P state. So I'm guessing I'm showing this one. The L of 1 M sub 0, and of course there is a plus or minus 1. So I'm showing L1 M0 right now. Of course, there's a normalization constant, comes theta, and for plus or minus 1, there's always a pattern to this. Like, okay, as I look at a different answer, the coses will turn into sines, and now that I've got an m quantum number, I'm going to have an e to the I m phi, so that's plus or minus phi. Now notice I didn't have a phi function for the m sub 0, but why would I? E to the 0 is 1. All right, so I'm thinking that that should be fair, that you should be able to know that. You notice that you don't really need to memorize anything. Okay, so I got to remember to do this, but now you're seeing the m of 0 and the m plus or minus 1. Now you may notice that the m plus or minus 1 do not quite look like p states, px and py states. The m sub 0 is a pz state, but the m of plus or minus 1, those do not look like px or py states. I'm going to explain that when we get to the hydrogen atom. But it's not a mistake on my part. They are not quite px and py states. Let me go ahead and just, I can't resist. I'll go ahead and tell you. Px and py states are linear combinations of these. So here, maybe don't write these down, but px is something like the wave function of m equals 1 plus the wave function of m equals minus 1 in py. I might have that reversed, by the way. I better check that out. M equals 1 minus the wave function of m equals minus 1. That doesn't look right. Anyway, so linear combinations of the plus and minus 1 are where you get px and py. Now, I maybe just forget it for now. We're going to cover this again. I'm just previewing. I just want you to understand why that L equals 1, M equals plus 1 or minus 1, why do they not look like the P states you're used to? That's because we usually write them like this, but we're going to cover that in the hydrogen atom. I don't want to get stuck on this right now, although I just did, didn't I? Anyway, so let's move on to the D states. So now we've got L of 2 and M of 0, which is a dz squared, and so I'm drawing that right there. And of course, the same thing will happen with the L of plus or minus 1 and plus or minus 2. Okay, I better go ahead and write the wave functions. There's a normalization constant. 3 cos. I always start with the cos, and it's a little bit more complicated. Now, it's a little bit more complicated than the pz state. So this is pz, this is dz squared, and it's more complicated. But it has to be. It's not the same function. Now, that also reveals something about why does this have rotate? Why did this dz squared and this pz, why did these have rotational energy and the s doesn't? Now, again, the s state, I have a hard time imagining how this particle isn't moving in a circle in this, literally inside of this circle. That's weird to me. But notice when it came to pz and dz squared that there's lots of nodes. We know that nodes are associated with an increase in kinetic energy. So the S state has no nodes, therefore it has no, in this case, rotational energy. The P and D and on and on and on, those have nodes. And therefore they do have rotational energy. I just can't, personally, I just can't visualize it. Other than looking at these images, I just can't visualize why a node means that you're rotating and no nodes means that you're not. I just don't see that. But I can derive it and accept it to the best of my ability. Now, the reason that the dz squared is more complicated than the pz, other than just it's a different function, is that it has to have more nodes. And so that's why cos and cos squared. Now, let's look at the other d states. We've got, and now as we go further, I'm going to pick up some sine functions, and that makes me more comfortable. I just basically expect that. And of course, we've got an m value, so we have our m function. And I can imagine that as cos turns slowly into sine, for plus or minus 2, you get sine squared. And then e to the plus or minus 2 I phi. There you go. Now, beyond this, of course, are the F states, which would be like lanthanides on the periodic table, but I don't think that we need to worry about those any further. I think we can just move on, and let's do some examples, tell you what. So I'll make that go away. let's do some examples of something, you know, I will give you an example of something I'll put on a test, and I've done this on your homework already. Let's just work some wave function questions. So let's put them into the Schrodinger equation and show that they're solutions. That, of course, is the 3D kinetic rotational Hamiltonian operator. Blah, blah, blah. That's a lot to say. Let's just plug them in. Now, of course, we're not deriving any of these. I don't, actually, I know how to derive almost everything up until here, but these I have no idea how to do. I'm personally satisfied by plugging these in and showing that they work. And again, you've already done that on homework, or maybe you have. Maybe I'm assigning it now. I don't know, but that's good enough. I think that's fair, right? So let's do some problems with that. And then there's one or two other kind of interesting little tidbits of information we're going to cover. We'll probably end a little early. And then next class, hydrogen atom. All right, so what can I do? What can I do with this? Let me write down. Okay, let's start with, sorry, I am a little flummoxed here. What do I want to do? I want to do kind of a harder one. I don't want to do the S state because that's like kind of stupid. Why don't we do an M sub 0? Why don't we do this one? Let's do this one. Let's do L1M0. Okay, so what will happen is that we are going to show that sine. Okay, so remember that this is the rotational kinetic energy. Okay, so now we should have our wave function. And it looks like I'm doing an eigenvalue thing. Okay, so now let's add in the, oh God, sorry, I got lost in my notes here a little bit. 2IE over h bar squared sine theta squared that's I'm obviously a little off today, sorry about that. Okay, so recall that what you're seeing here, this is the rotational part. This is the rotational kinetic energy. We had made several derivations with it. We had several manipulations, a lot of algebra, this and that. So I know that maybe this doesn't even quite look familiar. This is the wave function of theta. This is the wave function of theta. So this may not look familiar to you, so I don't expect you to memorize this if I have you work a question, because the way that this can be expressed, the way that this Hamiltonian can be expressed so many different ways, you've already seen some manipulations. It would be very confusing to know how to start, so I'd make sure that you know where to start to answer the question. I hope that you just understand from my, I don't want this just to be a math exercise. I hope you understand that you're looking at the kinetic energy in spherical coordinates. Okay, now recall that so we did this just a few moments ago, right? Where this whole thing is the theta part, and the phi part is here. The phi part was just reduced to m squared. And I've already told you that m is 0 because I'm using the m equals 0 wave function. So now what I want to do is I want to verify that this is going to work. Now I can already see, one reason I got a little bit cross-eyed earlier is that I don't see how the energy is going to be wiped out here. See, there's energy, but I don't see the energy here. Okay, but now I gotta recall that I have a formula for energy. Energy is L times L plus 1, h bar squared over 2I. You know, I've already told you L is 1, so that's 2h bar squared over 2I. Okay, so on my next step, you see that's gonna, basically gonna wipe that out. Okay. All right, again, this is the kinetic energy operator. I've told you what wave function. I've given you the energy. Now let's just do the next step and verify. Okay, so I've got sine theta, derivative of sine theta. Okay, we all know that the derivative of cosine is minus sine. Okay, the normalization can come out. I've seen some of you do this before. Don't think that that means you're subtracting sine squared. You're taking the derivative of minus sine squared. See what I mean? It's easy to think like, oh, derivative minus sine squared. That's the derivative of negative sine squared. That's different. Okay, so we've done that. Okay, now I've got 2IE is 2h bar squared over h bar squared 2I. Let's see, that wipes that out. You see, that all is just 2. Okay. Next step. All right, we're back here. There's really not much else to do. Okay, the derivative of sine squared. So I've got minus n. Okay, the derivative minus n sine theta. I just brought the minus sign out. Okay, the derivative of sine squared is 2 sine theta. The derivative of the inside function, the derivative of sine is cosine. Then there's all this jazz. And is it equal to 0? I hope so. Now let's check this out. I've got minus 2n. That's sorry. Let me be judicious for what I put together. Minus 2 sine squared, sine theta squared, n cos theta plus 2, I shouldn't write all this down again, but I'm obliged. Okay, that plus that is 0, and we're done, because this is that 0. Okay, so there you go. The point of this was to look at this miniature Schrodinger equation for theta, the dominant one. Remember that the phi part came in here as n squared. I plugged in some specific information for L equals 1, n equals 0. So the phi part is its contribution of n squared was 0. And then you just go from there. And you can also see that this is obviously an eigenvalue equation. And it's a little daunting, it's a couple of steps, but it does work. And of course, why would I be talking about this unless it works? Okay, now there's one last bit to cover. Sorry, let me check out Alexa. I've got 5 minutes left. And I want to show you one last neat thing. And again, I don't know that I would hold you to this on the exam. This is kind of down a rabbit hole of very specific, detailed information. I'm aware of that. But I want to show you this because it's kind of neat. Some of you may end up in grad school. Sorry everyone, slight problem with the camera. All right, so this last bit I want to show you is to get a big picture understanding, a little bit more about how all of these things work together. How does L work with M? Because right now it's just a bunch of quantum numbers, energy, this and that. But let me remind you that these angular momentum are axles of a wheel, right? When we were doing 2D rigid rotor, we were always talking about JZ because the action was in the XY plane, but my body is the axle, right? And the axle is the angular momentum vector. My body is pointed in the Z direction. That's why, even though the 2D rigid rotor was in 2 dimensions, in the x and y, everything was like with angular momentum is in z. So everything was expressed in z, even though there's no z. That's how it works. Let me just show you how it works for the whole 3-dimensional thing. Now, to do that, let's work with a d state. Let's work with an L equals 2, and I'm going to show off an m equals 0, 1, and 2. What I'm going to show you is what that means in terms of the rotational motion. And to do this, I need to describe the axle, right, the angular momentum vector. And I need to describe how long that vector is. Now, the energy in 3 dimensions is L times L plus 1 h bar over 2I, h bar squared. Okay. Now, recall that there's no other type of motion except rotational kinetic energy, and therefore, I'm going to say that there's a total angular momentum, which is J, big J, instead of little j. We had little j for 2D, but now that we're in 3D, we're going to have a big J. We're going to have a big J operator. And momentum squared over 2 times mass, but mass, of course, is in the moment of inertia. So it's similar to what you've had before. It's just it's got an I instead of an M for mass. Okay. Now, recall then that if you just do some algebra, J is h bar square root of L times L plus 1. Now, notice the similarity. I know that you're looking at this thinking like, okay, well, that's something new. Remember that when we had 2D rotation, it was very similar to the free wave because the momentum was just h bar m. And of course, for free wave, momentum was just h bar k. So I tried to make the 2D look familiar by pointing out how similar it was to a free wave. Its momentum was just h bar m, where m is the new k. It's the new quantum thing for momentum. Check this out. H bar L times L plus 1. If it wasn't for that L plus 1, you would have the square root of L squared. In other words, this thing is actually just about h bar L. H bar L, h bar m, h bar k. It's actually really similar, except it's not quite the same because of that L plus 1, but it's not that far off. Okay. So it's a little perturbed, but reality is it looks kind of the same. Just wanted to point that out. That everything is always like momentum squared over 2 times something with mass. It all looks the same. Sometimes the letters change, but they're really quite similar. Now, as I mentioned, I wanted to show you a little bit about how all these things work together in terms of describing the actual motion. Just like JZ describes our 2D, in 2D on the XY plane, but the description is based on the axle, which is my body, which is in Z. Let's now do the same thing for the D state. Okay, now I'm going to start with the m equals 0. So I have to draw a z-axis, and here is an x-axis and a y-axis. I'll just assume that the motion is along the x-axis. You see, the reason I'm saying that the axle is on the x-axis is that the component, the z component has everything to do with the phi angular momentum. So for an m of 0, I'm talking about the I'm talking about the jz component, right? So the jz component is 0 because m is 0. It's right here. Okay, that means that the axle is along this direction, and the length is h bar times square root of L times L plus 1. Now, the length of the vector, the longer the vector, the faster it rotates. Remember that the length of the vector is the angular momentum. The more angular momentum, you have to be moving faster. Okay, with that, so now you understand how fast it rotates, but to have an m of 0 for this D state means that you're not doing this. It means you're doing this. Right, you get that? if the axle is pointing in the y direction, it means you're doing this. 90 degrees to what we were doing in the xy plane. Now, for an m of 1, what you have to have now is you have to have a component on the z-axis, right? It's right here. You now have to have 1 h-bar of angular momentum in the z-axis. Now, what that means is your vector is just as long, your angular momentum vector is just as long, but now it's slightly tilted up. And just like before, when you're rotating this way, in this case, God, this is not, I'm scared. In this case, you're doing this, right? You see, I'm tilted slightly. So the rotational motion is kind of like this. Here, it was purely, the rotational motion was purely in the, just like I did before, but now it's building up a tilt. And when you get to the m of 2, so there's 1, there's 2, then it's like this. And again, the length of the vector is just as long, and I'm not about to twist my body like you just saw a minute ago. But even more so. So it's like this, there's a slight tilt, and then there's even a greater tilt. And so there you go. And of course, we're talking about an electron. It's on a string, and there you go. So again, I just wanted to point out how the L quantum number tells you how long the axle is. That's related to how fast it spins. The more L, the faster it spins. And the direction has a lot to do with M. It tells you how it's tilted, how it basically like tilts this way. And that's about it. And you've seen wave functions, and there's really nothing else, not much else to say. With that, next lecture is hydrogen atom. One more day of a Hamiltonian that goes across the board, and we're never going to see that again. So tomorrow is kind of, in many ways, tomorrow is kind of it. So I will see you all then.